Okay, so I think I'll start with a quick review of. It's been a while, so I'll start with a quick review of what we were doing. Um, we were looking for a quantitative way to figure out whether the mixing is good or not, and um, the way we found was um, essentially two formulas that define the boundaries in which the gas is either completely dispersed or the impeller is flooded or the impeller is loaded. So those pictures, I think I showed um, from the book. Maybe I should just um, yeah. So uh, this is the picture that I had shown to you. On the left, we have the worst possible case of impeller loading, which is something that typically happens at high gas flow rates.
So I guess your screen isn't being shared yet.
Oh, mm. Is it shared now?
Yes.
So, what we were trying to do was to find a quantitative way of determining. So, first of all, we talked about the fact that the flow can be in the following three qualitatively different patterns, depending on, among other things, the flow rate of the gas and the impeller speed. And what this figure is showing is that basically, starting from the right, if you have a relatively low gas flow rate, let's say on the right hand side, that's the picture you have. Well, let's start from the left actually. Let's say you have a very high gas flow rate and a very low impeller speed. Then, as you increase the impeller speed, keeping the gas flow rate fixed, you will move to the pattern in the middle, which is called impeller loading. And you can see over here that gas is getting mixed above the impeller, but there is no recirculation of gas that is taking place below the impeller. Yeah, the region below the impeller is completely quiescent. And then finally, if you increase the impeller speed even further, then recirculation will start even at the bottom. And this is the desirable picture that you want. This is called complete gas dispersion. So the undesirable picture on the left is impeller flooding. The picture in the middle is impeller loading. And the picture way to the right, the desirable one, this is what you want, is called complete gas dispersion. And if the gas flow rate is fixed and you're increasing the impeller speed, you move from the left to the right. You just invert it by keeping the impeller speed fixed and increasing from a very low gas flow rate to a very high gas flow rate. You move from the right to the left. So gas flow rate and the impeller speed, they have inverse effects. I mean, high gas flow rates cause flooding, and high impeller speeds give you complete gas dispersion. And what we found was that uh, all of these effects could be captured by defining two numbers, which were called the gas flow number, which is FLG, which is defined as, or it's also called the aeration number. It's the gas flow rate in liters per minute divided by the flow rate with which the impeller is pumping liquid. And this is Fg divided by NIDIQ. And the other number we need is the Froude number, which appears in your transport phenomena course, in fluid mechanics section, section 1. It is the ratio of the inertial force to the buoyant or gravitational force, and that is essentially given by rho vi squared, which is the magnitude of the inertial stress, and rho g di, which is the magnitude of the pressure due to gravitation. And the ratio of these gives you vi squared over gdi, which is equal to, since vi is equal to n sub I di, the impeller speed, impeller tip speed, you end up with ni squared di g. Now, the way to do these assessments of whether you have flooding, loading, or gas dispersion is basically given by two formulas. The two formulas actually define the two boundaries. So it is shown graphically over here. So my notation here is different from the one in the book. The book doesn't give this graphical picture, but it's easier to see what's going on graphically. The book only gives the formulas. And I'll just go through one formula. One formula given is, let's say, the one that I'm calling 1 here. And this defines the, the, the function FL under bar of G. Under bar means lower limit. And basically, if the flow number is lower than FL under bar G, you have complete gas dispersion. And if the flow number is bigger than FL under bar G, you have impeller loading. So, not written very clearly, so let me rewrite this. This is impeller loading. And this function is given by this FL under bar G. This is a function of the Froude number as well as the ratio of the impeller to the tank diameter. This is an empirical formula, but it is given in the form of powers. So it can be conveniently, if you rewrite it, if you take the logarithm of both sides, you basically get a straight line. So just below that, I have written it in the form of a straight line, which you can see has slope of obviously of 0.3. If I plot it against the Froude number, if I plot FL of G versus the Froude number, you can see that FL under bar of G will basically be a straight line of slope 0.3, and it'll have a y-intercept that depends on di over dt. So this is a convenient way to see what's happening. Similarly, there is another formula given for the upper limit, which I call FL over bar G, that defines the flow number at which the transition from impeller loading to impeller flooding takes place. And that is given by this formula over here. FL, so essentially FL over bar G is essentially 30 times di over dt, 3.5 to the power 3.5 multiplied by the Froude number. So when you take the logs, you can see that now the log of FL over bar G versus the log of Froude number will have a slope 1. So that is why you can see the red line that is drawn over here has a higher slope. This line has slope 1, and this line has slope 0.3. Okay, and now I think we're sort of ready to go. So keep in mind that these graphs are plotted with fixed di over dt, right? So you can see that for different di over dt, the graphs will change, because as you can see, di over dt determines the y-intercept in these graphs, right? So for example, this is your, this here is your y-intercept for FL under bar G, and this here is your y-intercept for uh, FL over bar G. So with that background, you can clearly see that as I also pointed out, there are two kinds of problems that you can think of. One problem is where you are operating under good conditions, okay, say complete gas dispersion, and let's say suddenly your impeller speed goes down. If that happens, then basically you will follow the path shown on the green line. Oops. This is should so the first example that we will consider, numerical example, is an example in which the system is operating quite nicely in the complete gas dispersion regime, and then suddenly something goes wrong with the impeller. Because the something goes wrong with the impeller speed goes down, everything else stays the same. The gas flow rate, um, the obviously the geometric dimensions, di, dt, these all remain the same. Only the impeller speed goes down. And when the impeller speed goes down, as you can see approximately, you can sort of see what's going to happen. If the impeller speed goes down, we'll do this numerical example in a minute, you can see that the Froude number will go down, and the aeration number or the gas flow number goes up. So the Froude number goes down because n sub I appears in the numerator, and the aeration number goes up because n sub I appears in the denominator, right? So um, basically, you expect the path to be of the type taken by the green graph, green arrow. It can either go to impeller loading or it can go to impeller flooding. Another possibility, which we will also look at, I'll point out to you, there is a problem exercise at the back of the book, is one in which the impeller speed stays the same, but suddenly in the middle of the run, the gas flow rate goes up. And that is equally destructive for good gas mixing, and that is represented by the yellow arrow. So the yellow arrow pointing vertically upward is showing you the path that one could conceivably take if you were to increase the gas flow rate at constant n sub I. And the green graph shows you the disastrous path that you can take if you decrease n sub I at constant gas flow rate. So let's take a look at both the numerical examples. These are both actually quite related to what actually happens in a reactor. So the first example is actually a solved example in the book, and this is the example in which the reactor is running fine, but then suddenly at a certain time the impeller speed goes down due to a mechanical problem in the bearings. So even if you were operating in the complete gas dispersion regime originally, this problem in the bearings leading to lower impeller speed may cause you to move in the undesirable regimes of either the impeller loading or the loading or flooding regimes. So let's go through the problem which I've actually already covered last time. So basically, they begin by giving you that a fermenter of diameter and liquid height 1.4 meters. So they are giving you the tank diameter dt, and they are also giving you the liquid height HL. Both are equal and 1.4 meters. So this is also an illustration. If you go back and take a look I told you the typical dimensions of the reactor. The height is approximately in the same neighborhood as the diameter. It goes up actually. The height is 3 times the diameter in some industrial bioreactors, but in most lab scale reactors, this relationship holds. They also tell you that the impeller diameter, it's a Rushton impeller of diameter 0.5 meters and off bottom clearance 0.35 meters operated at 75 RPM. So they have given you the impeller diameter DI as equal to 0.5 meters, and the off bottom clearance was what we called C sub I, that is given as 0.35 meters. And then they also tell you that it is operated at the speed 75 RPM, so N sub I is given to you as 75 RPM. Okay? So now the original conditions in which the fermenter was operating. The fermenter broth is sparged with air at a volumetric flow rate of 0.28 meter cube per minute. So F sub G is given to you as 0.28 cubic meters per minute, or basically 280 liters per minute. And halfway, this is now the change that happens. Halfway through the culture, some bearings in the stirrer drive begin to fail, and the stirrer speed must be reduced to a maximum of 45 RPM for the remainder of the process. So this is what I was telling you, that in this problem, there is an abrupt change in N sub I, and this is like the green curve that I had drawn, and they're asking you, they're telling you, is the gas completely dispersed under normal operating conditions? So normal operating conditions would be when they are operating at 75 RPM. And then he says, after the stirrer speed is reduced, is the impeller flooded or loaded? So this is N sub I equal to 75 RPM is what you have at the beginning, and N sub I equal to 45 RPM is what you have later on. So going back to the picture that I drew, this is straight off a problem of the type that is shown graphically here with the green arrow, right? So first thing they're asking you is, under the original operating conditions, is your initial point in this region? Is it in the complete gas dispersed region? Are you in the desirable place when you were originally operating? And second thing is, when the impeller speed goes down, where do you end up? Do you end up in impeller loading, or do you end up in impeller flooding? Right? That's so basically, do you end up here, or do you end up here? Where do you end up? You know you're going to move somewhere in that path, but where exactly do you end up? Is that part clear? So if the question is clear, we can proceed now with the answer. So
Yes, it's clear.
So basically, now the idea is pretty straightforward. I mean, I will not follow. I'll just give you the idea. So the first thing that should be clear is, so you can see that basically what you need to find out straight away, given the graphs that I have drawn, is you need to know what is the value of FLG, and you also need to know what is the value of FL under bar G. This is to answer problem A. And why is that? That's because, go back here and take a look. Basically, it is the value of the flow number relative to FL under bar G that determines whether you are in complete gas dispersion or not. So the first question is saying, are you completely dispersed? And the answer is, well, let me just find out my flow number and let me see where it stands relative to the lower boundary FL under bar G. If FLG turns out to be lower than FL under bar G, then I'm good. If I'm above it, then I am in impeller loading. So that's as simple as that. Well, all the material to do this calculation is already given to you, right? I mean, the flow number is um, uh, so the flow number is n sub I divided. Sorry, the flow number is f sub g divided by n sub I d sub I cube. Is that correct? I hope I got it right. Yeah, and the fruit, and this is right, n sub I squared di over g. So this is dependent on, this is a function of the fruit number and di over dt. And you can easily see that all these things can be calculated. You are given the flow rate, you are given n sub I initially, you are given d sub I, so you can calculate FLG. And the fruit number we just found out was n sub I d sub I squared divided by g. This also can be calculated, and we can find out di and dt. So we can calculate this, and if you do the calculation, you actually find that the flow number is below the lower boundary, slightly below. So initially, you are operating in the desired regime of complete dispersion. So this is how you would solve the problem. Okay. So essentially, in part A, ask the question: is FLG less than FL under bar G? Everything else is given to you. You can calculate all of these. This is a function of the fruit number and di over dt, and both of these can be calculated. Now, in part B, he says that suddenly I have reduced the stirrer speed. Is the impeller flooded or loaded? Now, in this problem, once again, it's the same story, except that whether it is, but now he's asking you that, okay, so actually when you solve the problem, you will see that your answer turns out to be very, very close to the boundary. In other words, originally, it will turn out you're operating literally at the boundary. So it's no surprise that an almost 50% reduction of the impeller speed uh, will take you away from complete gas dispersion. And the only question that remains is, where do you end up, in impeller loading or impeller flooding? And it turns out that when you do the calculations, and the calculations now have to look not at the lower boundary FL under bar G, but at the upper boundary FL over bar G, because that is what determines whether you're operating in impeller flooded or impeller loaded regimes. So now you go back and essentially ask the question, part B. You have to basically ask the question, this is the new number, right? So this is uh, is it less than or bigger than? So now, of course, you'll have to do the calculations with the new conditions, right? You'll have to do the calculations with n sub I equal to 45 RPM as opposed to 75 RPM. So the first problem is done under the original conditions, and the second problem is done under the new conditions. This is 75 RPM, and this is 45 RPM. Okay. So you can see that under the new conditions, as expected, uh, the flow number will be higher simply because in the flow number n sub I appears in the denominator. Okay, but the FL over bar G will so basically this number will have increased as shown over here. So back to your flow number will have shifted essentially to a higher number. So if you were operating somewhere here, it'll end up that you are operating in the left region. And when you do the calculation, it will turn out that um, the answer is essentially that you are operating in the flooded regime. So is that part clear, or should I go through the numerical calculation? Did you get the idea of what the problem is, or do you want me to work through the numbers?
Yes, sir. Yes, sir. I got it.
Is there anybody else who would like to comment?
So it's clear.
Okay. So let me now point out uh, the this is uh, the inverse to this problem. By inverse, I mean not inverse, but the complement to this problem. In this problem, uh, what happened was that suddenly in the middle of the run, the impeller speed changed. If you go to exercise 8.1, uh, this is what happens when suddenly the gas flow rate changes. And these are both realistic scenarios. By realistic, I mean that they do happen. Uh, so the second one, actually, the exercise is a bit more realistic than this one. Uh, so look at problem 8.1. This problem is uh, one in which there is nothing wrong with the impeller speed, but the gas flow rate suddenly goes up. And the reason for that is, roughly speaking, that when you do like a batch culture, your cell density is constantly growing exponentially, throughout the course of the run. And it might so happen that after the first 5, 7, 8 hours, the cell density becomes so high that the flow rate at which the sparger is delivering the air is simply not sufficient, right? Not sufficient for the high cell density that has now developed. So then you are compelled to increase the gas flow rate in order to make sure that the high cell density is compensated by a higher availability of oxygen. So that's what this problem is about. It says that an aerated, this I will ask you to do on your own. An aerated bioreactor of diameter 1.2 meters is used for batch culture of some strain. The reactor is stirred using a Rushton turbine diameter of diameter zero point 0.4. Now here's where the problem starts. At the beginning of the culture, when the cell concentration and cell oxygen requirements are relatively small, right? Because how much oxygen you need kind of depends on how many cells you have. So initially, when you have a very, very small inoculum, your oxygen demand is very, very small. And she says the stirrer operating speed of 110 RPM is just sufficient to completely disperse the air bubbles. So she's telling you that the system is completely dispersed at the beginning. Okay. Now, she's not telling you exactly how much it is, but she's simply telling you that whatever the gas flow rate is, it is adequate. But then she says towards the end of the culture, when the cell density is high, it is decided to double the volumetric flow rate to supply more oxygen. So now you've simply doubled it. And the question that is being asked is, Well, if the flow rate doubles, will the impeller be flooded or loaded under these conditions? And if it is not, right, suppose you find that it is, basically it is safe. The second question is saying, now that you have gone into and the answer will turn out to be whatever, loaded or flooded. And the second question is saying, now that you are in this undesirable place, how should you crank up the stirrer speed to bring yourself back to complete gas dispersion? So, in terms of our picture here, this problem is basically starting off by telling you that you are, let's say, somewhere. First question it asks is, it tells you is you are here, and then it tells you that suddenly the gas flow rate went up. Do you come here in the impeller loader regime, or do you end up in the impeller flooding regime? Which one of these two do you end up, because you have cranked up the gas flow rate while everything else was the same? It'll turn out to be one of these two regimes. But the second question is now saying that now that you know that you're operating in an undesirable regime, how will you crank up the N sub I to come back? So supposing you were in the impeller flooded loaded regime, you would have to increase N sub I to come back somewhere here by this path. And that is what the problem is asking you to do. Okay? So I think that should be enough for you to practice at least one problem. And you may also want to consider um, um, well, the rest of it. Um, so you may want to try 8.1 and 8.3a. They're not ready to do, so you may want to try 8.1 and 8.3a. These are both related to what we covered today in the lecture. Okay. So, are there any questions? If not, we'll move on to the next topic. So, we have covered one of the four topics that we were supposed to cover, which was um, how is gas mixed well, and we're ready to move on to the next topic, which is how do we make sure that the solids are mixed well. So, are there any questions? Okay. So the next topic, again, so roughly speaking, what we are doing in each section is we're finding out what is the impeller speed required to satisfy some desired requirement. What we just went through was basically finding out what is the impeller speed required to keep the gas well mixed. And now we're going to move on to what is the minimum speed we need to prevent the cells from settling at the bottom of the reactor. And after this we will go on to what is the impeller speed which is required to keep the liquid phase well mixed. And then finally, when we have all these impeller speeds, we'll find out. So we'll take obviously the maximum of these impeller speeds because it satisfies all three requirements. And then we'll find out what is the power that is required to maintain the speed. What is the power that is required to keep the impeller operating at this impeller speed? Okay, so this is the second topic. And so we're now moving on to the topic of um, uh, actually I'll make this just complete suspension of solids, which in this case almost certainly means cells. And I'll make that more precise in a minute in reactors. So it's not always cells, but here are the main. So basically, before you can understand it, uh, it's a good idea to have some idea of the length scales, uh, the size of the cells. So in bioreactors, solid particles appear in a wide variety of sizes. So bacteria, for instance, are on the order of 1 micrometer. If you talk about yeasts, then these are on the order of 10 micrometers. So let me just point out where I'm going with this. What I'm trying to say is that typically this suspension problem appears in reactors which have solids of higher size. And the reason for that is the bigger the size of a particle, um, uh, the higher its terminal velocity. And I hope you know what the terminal velocity is, but I'll get to that in a minute. This is the velocity that is really attained in terms of settling. What is the final velocity they attain moving down? So the bigger the particle, the larger the terminal velocity. So in other words, the larger the tendency to move downward, and the more severe the problem of those cells settling at the bottom. So essentially, bacteria are on the order of 1 micrometer, yeasts are on the order of 10 micrometers. If you go to fungus, then they typically form large clumps, and these clumps are on the order of 1 to 5 millimeters. So you can see that this has gone up by a factor of 10 compared to bacteria, and this has gone up by a factor of 1,000. And finally, one more thing, which is not exactly cells. Another common is immobilized cells. These are basically cells that are put inside a plastic, I shouldn't say plastic, like a polymer embedded. So these are not cells freely suspended. They are embedded either on inside a particle or sometimes on top of a particle. So the cells are basically rendered stationary or immobile uh, on a solid substrate. And these are also, I'm guessing here, number is not given, but on the order of 1 millimeter. Now, the important point is that um, for these two systems, it turns out that the terminal velocity is small. But for these two systems, the terminal velocities are quite large. And it is these two systems that give you problems, right? I mean, so it is only in these cases that you really have to sit down and do these calculations. Um, so, do I have to? Do you know what terminal velocity is? Is that familiar to you?
Yes,
Yes.
sir.
Okay. And is it clear that the um, uh, the terminal velocity of a larger particle is larger? Is that part already done? You're aware of it?
Yes, sir.
Yes.
Okay. So main point here is that the problem of a poor suspension is acute only uh, in fungal and immobilized systems. Okay. Now, with that background, let's just start the, the the method for doing this calculation. This is again empirical. Uh, this is so first this work will be done for ungassed, and then we'll modify it. By ungassed, I mean that many of these relations were derived actually by chemical engineers who don't necessarily always work with aerated systems. I mean, many of the systems are not aerated, right? The reaction is just in the liquid phase. And they may be working with, for example, instead of immobilized cells, they work with catalyst pellets. And all these theories have been developed essentially by people in the oil industry. And the biochemical engineers basically just came and applied them to their own system. So this particular correlation was originally developed um, by a guy called Zwittering. Uh, I think he I think he worked for Shell, if I'm not mistaken, the oil company. And later on, people in the bio business, I suspect, modified it to include for the effects of gassing as well. And basically, what he said was so. First thing I should point out is that uh, the meaning of the word just complete suspension, right, as opposed to complete suspension. By just complete suspension, what Zwittering means is he's giving you the bare minimum impeller speed that is required to just prevent the cells from settling onto the bottom, not for complete mixing of the solids, but for prevention of settling at the bottom. This is different. Uh, in order to have perfect mixing of the cells, you actually need much higher impeller speeds, which will be covered in the next section on good liquid mixing. If you have good liquid mixing, it will simply carry the solids around. And what Zwittering concluded, uh, based on experimental studies, was that this minimum impeller speed required for uh, just preventing the particles from settling, he calls it NJS. He said that it is actually always a function of, first of all, this is a function S, which I'll give in a minute, of impeller type, and di, the ratio of the impeller speed to the tank diameter, and the clearance, the off bottom clearance of the impeller divided by this, and then multiplied by nu L, which is the kinematic viscosity, which I will define more clearly in a minute. And this is X is percent solids. That means what is the weight of solids per 100 gram of suspension. So like, if it's 2 grams per 100 grams of suspension, you would say that X is 2%. And this is the diameter of the particle. Now notice that these powers are all low. So I'll put this in uh, I put this in green brackets because weak dependence. I mean, if you have like something to the power 0.1 or 0.13 or 0.12, it means that if that quantity increases, there is very little change. I mean, do you understand my point? I mean, for example, nu L to the power 0.1, um, if I increase even fivefold, there's hardly any change. It'll basically not even increase twofold. So it's a very, very weak dependence on nu L. But there is a strong dependence on this quantity, which is the buoyant effect, not surprising. So this is G. Rho P is the particle density. Rho L is the liquid density, minus 1. And this whole thing uh, divided, this is to the power, this is, you can see, to the power 0.45. This is, so it's approximately increasing at the square root, which is kind of strong. And then, of course, it is inversely proportional to the impeller. Um, I think I lost the connection. Um, can somebody tell me where was I when we stopped?
So we're discussing about how it varies as an approximate square root of J into rho P by rho L.
Okay. Um, so um, the strong dependence is on the, this is, you might call the buoyancy term.
So your screen is in
Yes,
share.
Giri.
Oh, um, let's see. Okay, so this is the buoyancy and this is the impeller diameter. So actually, it turns out that this is completely dimensionless. Am I correct? No, no, no. The impeller speed cannot be dimensionless. It has the right dimensions, though, 1/time. Um, okay, so let me just spell out this quantity S, this function, which depends on, so all of the dependence on the impeller type and the ratio of di over dt and ci over dt is encapsulated in this factor, which is covered in this entire portion, is covered in this entire dependence is shown in table 8.4 of the book, which I'll show in a minute. I'll, I will return to this in a minute. And nu L is what is called the kinematic viscosity. Actually, uh, this is actually defined as mu divided by rho. And as if you remember it, this has units of m, l minus 1, t minus 1, and rho has dimensions of mass, length minus 3. So you can see that actually m and m cancels out, and you end up with uh, uh, this will be L squared T minus 1. In other words, say meter square per second, which is the same as the dimensions of diffusivity. So this is known as kinematic viscosity. Kinematic viscosity, but it is also known as momentum diffusivity. So it's really the real measure of the intrinsic tendency of momentum to be transferred by diffusion as opposed to convection. Okay, so it's not viscosity alone; it is viscosity divided by rho that really tells you what is the diffusivity of momentum transfer. And x is defined as um, the weight percent of particles. This is the weight percent of particles, which could be cells or it could be immobilized particles in the medium. And this has units of, let's say, grams of particles per 100 grams of medium or suspension. Okay, and I think dp is particle diameter, particle diameter. G is acceleration due to gravity. Rho p is again particle density. Rho L is the density of the liquid, and di is the impeller diameter. So I have nothing more to add to that. This is, I can't remember now. Let me actually mention to you where I'm covering in the book. This is there it is. Okay. So section 8.8 is what we are covering right now. And this is the formula that I have just given you. This is equation 818 of the book. So this is uh, equation 818 of Doran. All right. Now, let me just show you the table that I mentioned. So there is a function S, which is a function of the impeller type, and di over dt and ci over dt. Well, that is shown as this table here. So let's see. So you can see that you have impeller type, you have on top, I'm looking at the rows of this table, it is giving you impeller type. Given the impeller type, given didt, and given CIdt, Ci over dt, you can calculate the value of S. This is a dimensionless number. Okay? So, for example, if you have a Rushton impeller, right, you're told that it is a Rushton impeller, di over dt is 0.33, and then any of these is valid. But you are also told Ci over dt is 0.25, then you narrow down S to 6.5. This is the way you would use it. Now, you can see that actually this is just a table, so many values are not given. Supposing I asked you for some Ci over dt or some di over dt, which was not in the table, how would you calculate it? And for that, people have provided some empirical uh, relations, and those are as follows. Um, so, first thing I should point out. So, so, uh, so keep in mind that the rest of this equation, right? Uh, only only this S depends on the impeller type and di over dt and Ci over dt. So, in other words, information about the type of impeller will simply determine S. The rest of the equation is the same for all impeller types. You understand my point? I mean, no matter what the clearance is, doesn't care, right? Everything on the right hand side. The only parameter inside this bracket, which also appears outside, is di. Everything else, the right hand side, which is I'm putting in green brackets, this entire thing, except for the di appearing over here, there is no overlap between the two. Okay, one side takes care of impeller type and so on and so forth. The other side takes care of uh, viscosity and properties of the medium, the properties of the solid, how many solids do you have, what is the buoyancy force, and so on and so forth. Now, having said that, I return now to the question of what happens if you get something that is not in the table, and there are two rules. These will be needed for solving the problems at the back. Uh, the first one is the first one explains the variation of S with di over dt. So let me first mention, for the sake of, you remember now, S was given as impeller type. It was given as a function of di over dt and Ci over dt. That is how the table was arranged. This was table 8.4. So, and what we are dealing with is extension. How do we extend of table 8.4, which provides, this is our goal. Okay. So the first rule is that uh, that S, that for fixed impeller type. So this is basically quantifying the variation, fixed impeller type, and Ci over dt. So if I fix this and I fix this, then S decreases inversely as di over dt to the power alpha, where alpha has been determined, where alpha is equal to 1.5 for Rushton impellers and 0.82 for marine impellers. So these relationships are required for extrapolating the data beyond what are the limited discrete values given in the table. And the second one, which is similar to this, is I should actually. The second one is for fixed impeller type. For fixed impeller type, and now let's say di dt. So I'm looking for extrapolation of ci over dt. They uh, actually, I'm sorry. No, there is no, there is no correlation given for this. This is only. So main thing is going back to the table. Um, so fixed di dt. C S increases. S increases with Ci over dt. So in effect, uh, basically what this is saying is that when you have high impeller speeds, okay, let's take a look at the first one. This is basically saying that when you have high impeller diameters, the higher your impeller diameter, the lower the speed you need, this NJS, to maintain the cells in suspension. So roughly speaking, high impeller diameters are good in the sense that at relatively low RPM, they will provide you, because when di over dt becomes large, S becomes small. When S becomes small, then your NJS goes down, right? So you need lower impeller speeds to maintain suspension. And just the opposite is true for uh, Ci over dt. The higher the value of Ci over dt, the higher the value of S. So that means the more off bottom clearance you have, the more S increases. The more S increases means NJS increases. So high off bottom clearances are not good. This is not surprising. It's basically saying the further the impeller is from the bottom, the more likely you have to find suspended particles at the bottom of the reactor, right? So this part is also clear. Uh, so now, this is a really straightforward problem. We can start. We can do the numerical problem, and so this is a straightforward uh, application of this problem. So this is basically, they're just giving you all the data, asking you to find out. So let's read. Basically, in a sense, they're asking you if the RPM at which the reactor is operating is good enough for keeping the cells in suspension or not. That's the crux of the problem. So the problem says that clump forming fungal cells are cultured in a flat bottomed 10 cubic meter, that's 10,000 liter fermenter of diameter 2.4 meters. So right here you are given, this is the volume given to you, and now they're giving you, this is dt equals 2.4 meters. So instead of giving you the height here, they've given you the volume of the reactor. You'll have to sit down and calculate the height if you need it. This is equipped with a Rushton turbine. Again, useful information. The diameter, this is d sub I, 1.2 meters, operated at RPM of n sub I equal to 50 RPM. You need the off bottom clearance. This is of bottom clearance. This is C sub I. This is how high the impeller is from the bottom. The density of the fermentation medium, you need this. This is rho sub L, right? This was there in the formula. The viscosity is required to need to calculate the kinematic viscosity, mu over rho. The density and diameter of the cell clumps. So this is what we call, this is rho P, rho P. This is the density of the cell clumps, and dP is the diameter of the cell clumps, both of which are required. And 600 nanometers is the size of the, this is dP, 600 micrometers, and this is rho sub P. And this is 40 grams of 40 grams of cells per 100 grams of suspension. So everything is given to you. Just plug it in. So first of all, as they say, you are given di over dt, which is 0.5. You are given ci over dt, which is 0.25. Right. So di is 1.2 meters, dt is 2.4 meters. So di over dt is 0.5. Ci is given to you as 0.6 meters. So 0.6 divided by the tank diameter of 2.4 is 0.25. So you have di over dt, you have ci over dt. Also know that it is a Rushton turbine. So you can come to this table over here, Rushton turbine. You are given di over dt, you are given ci over dt. You can find out S, which turns out to be 4.25. So there you are. S is equal to 4.25. Now just plug in the rest of the calculations, right? I mean, you have to do all the calculations in consistent units. The most important thing here is pick one set of units, either CGS or MKS. I mean, I prefer to use MKS, and just stick to it. 90% of your errors will be due to mistakes in units, because these are essentially simple empirical formulas. Um, if you plug in the numbers right, you will get the right answers. And then he just calculates them one by one. So this is, for example, the effect of mu L, right? Then there was a slightly weaker dependence of 0.2. This is d sub p, and then should be a dependence on 0.13. This is x to the power 0.13. This is dp to the power 0.2, mu L to the power 0.1. This is that long factor g times rho sub p over rho sub L minus 1. And right here at the bottom is that di to the power 0.85. He just calculates it, finds out that the NJS is 18.6 RPM, right? But he's already telling you what is the RPM at which he's operating, which is 50 RPM. And since 50 RPM is bigger than 18.6 RPM, everything is good, because this NJS is the minimum RPM you need to keep the cell suspended. And you're actually operating at almost 2.5 times the minimum RPM. You're operating at 50 RPM. So it says the operating stirrer speed is well above the stirrer speed required for suspension. The cells are therefore completely suspended. Is that part clear? I think that's all there is to this section. I think we will only have to change a little bit to include the effects of gassing, which I'll cover next time. So, so far we have done with without gassing. Actually, I should finish it right now. What happens with gassing is essentially you have to modify the formula slightly. This is the NJS. This is the NJS that we just calculated without gassing. And FGV is the gas flow rate in units of VVM, or gas volume of gas per unit volume of liquid per minute. So you can think of FGV, if you think about it, is essentially residence time no, this is dilution rate of gas. I mean, I should correct myself. Um, this is the easiest way to remember it is 1 divided by FGV is equal to the residence time of gas, approximately, in some way, one way. So all you have to do is, if you know this FGV, now you have a gas system, and this FGV is expressed not in liters per minute, but in volume of gas per unit volume of liquid per minute. So, for example, if you had a 2 liter, if you had 2 liters of liquid in a reactor and 1 liter of gas per minute flowing in, your VVM would be 0.5 per minute, because you would take 1 liter of gas per minute and divide it by 2 liters of liquid. So you would say that basically, essentially 0.5 volumes of the liquid phase are being passed through the liquid per minute. That's another way of looking at it. So essentially you modify, for didt equal to this much, you use this formula. For didt equal to this much, you use this formula. That is all there is to it. Okay, I'll cover this in more detail next time. So if there are no questions, then are there any further questions on this topic? I mean, I'll probably give you some problems to do on this topic as well. Let me also finally, since we have only 5 minutes, regarding the minor will be on Saturday and Sunday. It will cover, I will ask questions similar to those on the homework as well as the 2 papers that I have given. So, is everybody good, or do I need to have a special session on the homework problems?
So it would be great if we could have like a short discussion for the problem.
Uh-huh. So that'll have to be in some period in the evening. All right. Meaning after 5 o'clock, because otherwise we'll never have any consensus. So starting tomorrow, you pick up a time and send it, and then we can have like a 1 hour session. Maybe starting on today. It's already Monday, right? So maybe Wednesday. I'm told that Wednesday afternoons there are no labs.
So I'll talk to the students once and I'll let you know.
So
I'll
Wednesday.
message. I'll drop a text on the Teams.
So Wednesday after 5. Okay.
Fine, sir.
And the minors basically, it can take anything from 5 minutes to 20 minutes, depending on how much you have to say. I mean, if I figure out that you're clueless, I will close the matter after 5 minutes. And if I find that there is some depth, I'll push it and see where you stop. Okay. So 5 to 20 minutes, one by one, I will ask people questions. Okay. Anything. And when I say homework problems, I don't mean that I'll ask you to repeat the homework problem. I might ask some variation on that problem, right? I mean, some assumption you made, why you made, why did you do that, that kind of stuff. Okay. So see you on Wednesday, after Wednesday evening.
Sure, sir.
Okay.
Thank you, sir.
Thank you, sir.